And we are back. All right, today we are going to talk about bond polarity and dipole moments. So yesterday we talked about the molecule HF, where F is more electronegative than H. Fluorine's more electronegative than hydrogen, so it obtains a partial negative charge. The hydrogen obtains a partial positive. So we would say this molecule has a dipole moment. There's a center of positive charge, in this case around the hydrogen, and a center of negative charge, this point around fluorine. So what we also do is we use an arrow to represent dipole moment. So if we draw the molecule HF again, we point the arrow to the negative charge center. So point an arrow to the negative charge center, and then the tail of the arrow indicates the positive center of charge. So with this tail of the arrow, what you do is you just put a little tail on it, and it makes sense because this end looks like a positive sign. So this tail of the arrow looks like a little positive sign, so that indicates the positive part of the molecule. And then the head of the arrow here indicates the negative part of the molecule. And in general here, this electrostatic map, this red portion indicates partial negative charge. That red portion means it's electron rich, meaning it's attracting electrons, whereas the blue indicates the partial positive charge, or the region that's electron poor, meaning electrons are being taken away from that region. So any two-atom molecule that has a polar bond will have a dipole moment. However, let's say we have the molecule hydrogen, H2, that does not have a polar bond. Remember, the electronegativity difference between the hydrogen atoms is 0, so we would say that is a nonpolar bond, and a molecule like this does not have a dipole moment. And same with any diatomic. So same thing if we had F2, fluorine bonded to another fluorine, those electronegativities are the same, therefore the difference is 0, so that one would contain a nonpolar bond and would not have a dipole moment. So these are all two-atom molecules, but if we get to polyatomic molecules, atoms that have more than two atoms, it gets a little more complicated. So now we have water, and water is polar. The reason why it's polar, the different dipole moments do not cancel, even though it might look symmetrical. So the dipole moments do not cancel. So the reason for that is we can draw those different dipole moments. We know oxygen is more electronegative than hydrogen, so it has a partial negative charge. Each hydrogen has a partial positive. So we can write the two individual dipole moments from this first hydrogen on top to the oxygen, as well as the hydrogen on bottom. That also has a partial positive charge, and that's also pointing to the oxygen. And it might be easier to see if I also wrote it on the inside here. So what happens if you've taken physics? These two, what we would call vectors, add together. So if we add these together, we get one overall dipole moment pointing up towards that oxygen. So these are the individual dipole moments here. This is the overall dipole moment, and it's pointing towards the oxygen. So if you look at the electrostatic map, obviously the electron is the electron-rich region. It's pulling more of the electrons. It has a higher electronegativity, and then the electron-poor region is around the hydrogens, which have the lower electronegativities. And it's the same thing with NH3, ammonia. Now, it has three individual dipole moments, all pointing towards the nitrogen. And then so the overall dipole moment is pointing straight up towards the nitrogen atom. So once again, those dipole moments do not cancel. However, the presence of polar bonds does not necessarily mean the molecule itself will be polar. So for example, carbon dioxide, CO2, is symmetrical. It is a linear shape. So if you look at the individual dipole moments, each one is pointing towards the more electronegative oxygen. However, since it's symmetrical, if you add these two up, there is no overall dipole moment. So even though the electron poor region in the middle with carbon, it's balanced out by the two electron-rich regions on the sides by each oxygen. So since it's symmetrical, those dipole moments cancel out. So even though CO2 contains polar bonds, does not mean that it is polar. Another example of that is CH4, methane, carbon tetrahydride. So if we draw it out here, the central carbon in the middle is more electronegative. So each of the individual dipole moments are pointing towards the carbon. Then when you add up those individual dipole moments, they cancel out. Okay, so even though CH4 contains polar bonds, overall it is not a polar molecule. So this is all based on symmetry. So if we have a linear molecule with two identical bonds like CO2, those will cancel. Same thing with CH4 or any four identical bonds like CCl4. And we'll go over why this structure is the way it is. It's called a tetrahedral structure since those four exterior atoms form the corners of a tetrahedron. So all those dipole moments cancel. And then one that we will talk about soon, a planar molecule, where those three exterior atoms are in the same plane, those dipole moments would cancel as well. So the main thing I want to stress, the presence of polar bonds does not always yield a polar molecule. Those dipole moments can cancel out, so there's no overall dipole moment. Alright, that's all for this time. See you next time.